Well, good morning. How are we today? Well, we're going to talk a little bit about PCR. Let me look at my watch here real quick because if I go too long, I can't get it up the upload. So let's keep an eye on that. Anyhow, we talked a little bit, or you watched a video last time on PCR. So you should know that that's polymerase chain reaction and that it's used to take a small amount of DNA and make a whole lot of DNA. If you remember right, we talked about this back in chapter 5. And the guy who came out with this was a professor at UC Berkeley who um, was a big believer in Timothy Leary's use of LSD to expand your mind. Not a good ideal, but that's what he did. And he got into his 1952 Porsche and drove up into Santa Monica Mountains and picked up a 6-foot tall white raccoon, according to his book. And they had a conversation where they worked out this. His background was in biochemistry, and his passion was in archaeobiology with archaeobacteria. And so when he looked at those things, he was able to put the two things together. How do I take a small amount of DNA and make a whole lot of DNA that's just exactly like that DNA? Because his issue was he was looking at using DNA that came from particular individuals, and you couldn't keep going back and getting their DNA over and over and over again. They get mad at you for that. So what he decided that to do is in order for everybody to have enough DNA to be able to look at all this, he had to find a way to make copies of it. And he put his skills together and he came up with the idea of PCR. Now, PCR does a really good job of copying a piece of DNA over and over again so you have as much as you need. His unintended consequence was now that same technique is being used in forensics. It's one of the best or greatest things that's ever happened to forensics. He won a Nobel Prize in chemistry for this and has never really agreed with the idea that it was used in forensics. But this is something that it's been accepted in both courts according to the standards that we have out there now. At one time, if you had just a little bit of DNA and you tested it and it destroyed all your DNA and you didn't have enough to give to the prosecution or the defense, then you couldn't do that because both sides had to have the DNA in order to use it, in order to test it independently to comfortably come up with the same results. And if they did, then, that really made the cases a lot easier to solve. So with the use of PCR, which is accepted by the courts, you could have as much DNA as you needed, and therefore no one never really runs out of the DNA, which was very, very important. Because if you don't run out of DNA, then you're very good to have it for both sides. No one can say that did something wrong, okay? Then it comes down to, well, we had these two different companies. We have a company over here that's working for the prosecution. We have another company over here that's working for the defense. And they tested the DNA, but they did it slightly different. Well, that brought up the idea of what's that case that keeps coming back and back over and over again? Well, it's the O.J. Simpson case. So now we have a technique over here that's used by this company. We have a technique that's over here used by this company over this side. And it's just slightly different than the one that's over here. They come to the same result, but the process is just slightly different. So the good thing about that, or the bad thing about that, is that you come to the same result. The bad thing about that is that we tend to have a society where if you do something this way, and they say that's the right way to do it, then that means the other way is automatically wrong because that is the right way to do it. And then if this side over comes and says, well, this is the right way to do it, and that one over there is doing it wrong, then you have confusion in the jury. The jury says, well, how do I know which one's right and which one's wrong? And that is why the O.J. Simpson case is, again, very, very high on our areas that we look at over and over again, is because it said from now on, you must follow this particular procedure and only this particular procedure if we're going to accept that in court. And so over and over again, people do it the same way, the same way, following the same procedure in the cookbook, and it makes it great. So now the defense nor the prosecution can get up there and say, well, they did it slightly different, so that's why they have a different result, or that's why they have the same result, or whatever it may be. It doesn't matter. This is the way it's going to be done. Everybody's going to agree on it, and that's the way it's going to be, and we're going to move on. Okay? So that is the forensic side of that. From there, we get to recombinant DNA. Well, recombinant DNA is where we cut the DNA using restriction enzymes. Restriction enzymes are a commercial enzyme that you can buy that will cut at a certain section. What do I mean by that? Well, I have a restriction enzyme that will cut after 3 A's and 2 T's if they're connected to each other. If only if they're connected to each other. It won't do it after 4, it won't do it after 2, but it will do it after 3. So 3 A's and 2 T's, and always it will cut it at that section. So now I can make little sections of it. And that little section helps me to do lots of different things. I can take and insert something, or I can take something out, okay? That's why it's called recombinant, because you're recombining the DNA, okay? Well, what's this used for? Well, if I have diabetes, okay, and I cannot make my own insulin, I need something else to make insulin for me. To do that, they will take DNA and insert it into either bacteria or yeast, and they do this all the time. And they will take that DNA that makes human insulin and stick it into those bacteria and into those yeast. And they will start to produce insulin as a byproduct of whatever it is they're doing. It's the same way that we use yeast to make bread or beer, or we use bacteria to make lots of different things throughout our entire lives. Okay, probiotics are something that everybody takes a lot of. Okay, these things are good for us if we do it correctly. And that's recombinant binding DNA when it comes to the good side. However, with every sword, there's a double edge. Okay, so the good thing is that we can make all the insulin that people who have DNA need, who have diabetes need. We can do that all day long, and it brings down the price and everybody's happy. Okay, well, what if you've got a particular disease and you're really kind of the only ones who it's really affecting, a very, very small amount of the population? You know, using myself as an example, I'm colorblind. I have issues with the enzymes in my eyes not working properly. So if they took my DNA and cut out those particular genes that I need to make those enzymes, and made that chemical for me, and I could directly inject it into my eye, which would be very painful, I'm not going to do it, and extremely expensive, because to do this for one person is extremely expensive. So it makes it cost prohibitive to me to be able to do that to cure my certain issues. And on top of that, I don't want to be sticking a needle in my eye just so I can see the color blue or red or whatever color it is that I might want to see again. So it's not worth it to me. They have to find a better way for me to do that. So it can be done. It's just not really worth it. Now, the other part of that is that somewhere along the way, let's say I wanted to kill Mr. Cogswell and only kill Mr. Cogswell. I could actually take, if I could get a hold of Mr. Cogswell's DNA and make a virus that only attacks him and no one else. And therefore I could kill him that way. Again, it's very cost prohibitive, but it's out there, okay? So as we look at our bioethics unit, which is coming up, and we're going to go into that here in a few more classes, that's what I wanted to look at, is that for everything that we have out there that is great, that you're going to see that is great about the things that you have for these bioethics, that there's also the other side. What is the dark side of using whatever it is that you're talking about in a bad way, okay? So that's the bioethical section that we're going to deal with. So here we have PCR, we have the ideal that we can recombine and redo your genetics. Is there an ideal? You know, if you go back to Jurassic Park, just because you can do a thing, does that make it a thing that you should do? You know, if you can make dinosaurs come back, well, that'd be fantastic. However, you know, if I brought back a bunch of velociraptors and let them go in my neighborhood, I'm fairly certain that somebody's not going to be happy with me when they got eaten. So that's a bad thing, you know. But what if I could control them? Well, I'm not sure you can control everything that we put out there, okay? So as we look at this, that's part of the process I want you to think of when it comes to our ideals, okay? So I am going to go for a few more minutes yet and look at tandem repeats. And tandem repeats has to do with the ideal of shotgunning. There was a guy who worked for Oracle, and actually found Oracle, which is a big computer company, and he sold off his section, and then he decided he wanted to sell the Ocean Blue and map DNA of the entire world, basically. but it was very slow process, and because our DNA is very long, you know, our DNA, if you put it in the end piece to piece, would go to the moon and back 4 times. So that's just for human DNA. So he's looking at this DNA and he's going, boy, this is really hard to do. I can't really do this. So how can I make this thing go faster? So he came up with the idea of shotgunning, which is what we now call DNA typing. Okay. And shotgunning basically is looking for tandem repeats, 2A's, 2C's, 2G's, whatever it is together, and cutting and looking at those sections and pulling them out. And it pulls them out. And then once you have a section of DNA, it can then run it through a gel electrophoresis. And that is where we're going to stop, because we'll start talking about gel electrophoresis the next time we go. But those tandem DNAs, as we go through this, made the process fairly quickly. It used to take, you know, months and months and months to go through a DNA conflict and figure out what's in there and what's not in there. What this basically does is really makes it a matter of weeks that you can take any type of DNA out there and say, I want to know what's in the DNA of a horse. So they could take that whole piece of DNA and go through the whole thing fairly quickly in about 2 weeks. What used to take us months and sometimes years now only takes a few weeks. And it makes it very, very quick. It's not to the point that it's going to tell you exactly everything that's in that DNA, but it could match up species. What do you mean? Well, a human is 99.9% human, no matter who they are, no matter where you come from. We are all pretty much the same DNA-wise. We have 2 eyes, we have 2 ears, and so on and so forth. And that recipe is in our DNA, and it's 99.9% the same for every human that's out there. It's that 0.1% that makes us different, you know, gives one person blue eyes, just slightly off colored, you know, makes you so tall, makes you so, you know, your complexion of your skin this way or that way, makes your hair this way or that way, gives you the mannerisms that you have and the way that you talk and the sound of your voice and how you look at things. All these things come from that 0.1%. And that is where we're different. And what he did is that he looked at all that 99.9% of everything and said, that's just a recipe for a human. You know, I don't want that. What I want to do is focus on that 0.1% that makes each species different and each person different and each thing different, because that is where we're going to find the things that make us unique. Okay. So we'll talk a little bit about gel electrophoresis the next time, and we'll let it go at that. Okay.